Okay, welcome to the today's class. Today we are going to look at unit number 5, lecture number 2. Okay, so today we look at Shannon's expansion theorem. So it is a very useful theorem. So when we are discussing about the FPGAs, okay. So let us define what is this theorem, how this theorem is useful in order to effectively implement our logic circuits in an FPGA. Okay, so what is this theorem says that? Okay, what is the definition? Generally, this theorem, this particular concept will decompose a large function into a fewer variable functions. Okay, so therefore it expands, or this theorem says that a large function is decomposed into a fewer variable function. What does it mean that? For example, we have a function consisting of 5 variables: a comma, b comma, c comma, d comma, e. So a function is defined, any logical function, for example. Okay, if a logical function having 5 variables, it is possible to decompose this one by using 4 variables. It is possible to decompose this one by using 3 variables. It is possible to convert it into 2 variables. Okay, so therefore, why we need to convert a large variable function into a smaller number of variable function? That's the question. So the reason is that, for example, if you have a smaller number of, that means less number of input logic function in your hand, but if you want to implement a large function by using that small function, it's very difficult. Okay, so what is the possible way that we can convert the logic function to a associated or available logic small number of function is done with the help of this particular theorem. Okay, so for example, let us consider it in this way. For example, I want to implement a 4x1 multiplexer. Okay, but in my hand I have only in my hand is only 2x1 multiplexers are available. Okay, then but I need to consider that 4x1 multiplexer. But I don't have a 4x1 multiplexer in my hand, but I have only 2x1 multiplexer. Therefore, what I have to do, I have to convert my 4x1 multiplexer. I have to convert my 4x1 multiplexer in order to implement by using the 2x1 multiplexer. Right. So in this situation, the Shannon expansion theorem or Shannon decomposition theorem is useful. Right. So how can we do this one? Let us do with this example so that we'll apply the same thing to the other cases also. Okay. So let us consider for this particular example only. So what is the logic function? How do we define a logic function for the 4x1 multiplexer? Generally, we have to represent it by S1 comma S0. Okay, so this function is nothing but I0 into S1 complement into S0 complement plus I1 into S1 complement into S0 plus I2 into S1 comma S0 complement plus I3 into S1 comma S0. Okay, so this is how we can look at the Boolean function that is associated or bound by the 4+1 multiplexer. Okay, so if you want to implement this one, the 4+1 direct 4+1 multiplexer IC should be there, or otherwise the basic gates that we have to use. So we don't want to go for the basic gate concepts because we have a ICs are available. So we have to make use of that ICs only. Therefore, since I don't have a 4+1 multiplexer IC, 4+1 multiplexer IC we don't have, but we have only 2+1 multiplexers. 2+1 max only we have. So therefore, now how this 4+1 multiplexer is converted into 4+1, let us see by using the decomposition theorem. What this theorem says that? This theorem says that you have to take, you have to choose one particular variable from the given variables and keep aside and put in place of that particular variable by logic 0 or logic 1. Okay, the statement I am writing in this way. That means whatever the logic function that we want to implement, S1 comma S0, okay, if you want to implement, what you have to do is that we have to choose one particular variable. For example, I'm going to consider S1 is my variable. You take that S1 and place in place of S1 by making it by logic 1. That means we have to use f of 1 comma S0. So whenever I have a function f of S1 comma 0, you have to place instead of S1 by logic 1. So if you want to make this logic 1, and we have to keep S1 aside of that one. Okay, we have to provide the logical and between these two. Similarly, we have to take S1 complement it. Therefore, S1 we have to take outside S1 by complementation. So if you are using the complementation, then what we have to do is that you place in place of S1 by logic 0, comma, S0 is as it is. This is how we have to do. So this is what the theorem is expanding. The theorem is decomposing the large function into a smaller number of functions in this way. So let us understand more clearly about this. Okay, so it is just, you can simply understand that, okay, it is simply 2+1 multiplexer. For example, S1 is, I'm writing here some function x. Okay, similarly, I'm writing, for example, x0 is the function. So I'm using the S0 complement, I'm using x1. Okay, it is simply as simple as the 2+1 multiplexer, right? So therefore, what I can say that now I have a function something like this. Sorry. So I have an input is equal, for example, S is my selection line, S1. My inputs are 0 and 1. For the case of 1, I am considering about x0. I am considering about here is x1, right? So I'll produce my output signal function of S1 comma S0, for example. What is x0 here in this case? X0 is actually as simple as that. It is f of 1 comma S0. So this is actually f of 1 comma S0. So what is this one? F of, I think better I have to consider this notation. I will change the notation, for example. Okay, I want to write it, this is for S0 for notation, the 0 purpose I'm using this one. This is for this one. There is no problem at all. Okay, therefore 1, this is 0. So similarly, I'm going to write this is for logic 1 for the 1 case, but this is for the 0's case. So here is actually I'm considering 0 comma S0, right? So therefore, simply I have realized the 4+1 multiplexer by using some part of this one by using only 2+1 multiplexer. Now again, I need to consider about what do you mean by f of 1 comma 0, f of 0 comma s naught. Okay, so let us evaluate. What do you mean by f of 0 comma s naught? What does it mean? So which means that whatever the function f of s1 comma s naught, in this one, what I have to do, replace this s1 by logic 0. So what is the function that I have with me? So this is the logic function I have. Okay, I want to copy this one. Oh, sorry. What happened here? Okay, this is what let us consider. Copy. Okay, here you can consider. So what I have to do here is that I have to replace s1 by using s1 by 0. So s1 complement, what does it mean? S1 of 0, that means I will write it in this way. So I naught 0 complementation into s1 bar plus I1 into 0 complementation s naught plus I2 of 0 into s naught bar plus I3 into 0 into s naught. So what is the value of this one? It is simply I naught into s naught bar plus I1 into s naught, because the complement 0 complementation is 1. That's the reason why I'm writing here. This is 0. This is also 0. So therefore, what is the f of 0 comma s naught now? It is simply a 2 cross 1 multiplexer, as you can clearly understand this point. Okay, sorry, this is 0. This is s naught. Okay, so therefore, what I can say that this is simply 0 and 1, which is supported by s naught. Just here you can write it is I naught. Okay, this is what I'm writing. For this one, I am writing this is 1. So therefore, it is f of 0 comma s naught. Clear? Shall we write for f of 1? F of 1 then, f of 1 comma s naught. What is happening here? Again, the same function I can write. I want to copy this one, paste it here. What is the value of this one now? Any guess? So again, I'm going to write here is that
I2 S1.
yeah, I naught of 1 over the complement of s naught complement plus I1 1 over the complement of s of 0 and I2 of 1 into s naught complement plus I3 into 1 into s naught. What is the value of this one? 0 plus 0 plus this value becomes I2 into s naught complement, and this is I3 into s naught. Right, finally this becomes I2 into s naught complement plus I3 into s naught. So it is also simply 2 cross 1 multiplexer, right? Therefore, what I can write it here is that just take that one, 0 and 1. Here the selection line is s naught. The input is I2. Another input is I3. The function output is f of 1 comma s1, s naught. Right. We have to substitute this equation in this one, as we have mentioned that. Okay, this is what the equation. We have derived that this is the equation, right? So we have to substitute there. Copy, and then I want to paste it here. So what it says that Can I define what is this? Now we already know f of this one. So okay. So what is the logic diagram for this one? I have an f. I have a 2x1 multiplexer here, which is S1 is completed here, is 0, it is 1. It is nothing but f of 0 comma S0 I need to produce. Here is f of 1 comma S0 is produced here. So what is the f of 0 comma this one? We already defined. We already derived this one. So it is nothing but 0, this is the 1 by using I0, by using the I1. Similarly, I have to consider the same thing. This is for I0, sorry, I2, this is I3, 0 and 1. So this is connected here, this is connected here, this is S0, this is S0. So the finally we have f of S1 comma S0. Is it clear? So therefore, whenever we have available components with you, but if you want to implement a larger functions, then Shannon decomposition theorem is the best suitable way to implement this kind of approach. Clear? So this is the one example. So it can be applicable for anything. Okay. For example, let us consider the expansion of the theorem. Let us consider in this way. For example, I have a 4 variable function is there. Sorry, I have a, for example, 5 variable function. Okay. Now, for example, if I want to decompose into 4 variable function, how many number of variables I have to choose? The question is, I want to convert the 5 variable into 4 variable. So how many number of variables I have to choose for decomposition? How many variables I have to choose for decomposition? Any guess? That is, I have to 4 of, for example, A comma B comma C comma D comma E. 5 variables are there, but I want to convert it into 4 variables. That means I have to choose one particular variable. Any variable I can take it. For example, I want to take first variable. So how do I write then here that f of, okay, f of B comma C comma D comma E is nothing but what it says that A must be a complemented version. For that one, f0 I want to consider as a 0 and B, C, D, E. Are you agree with me? What I'm doing here is that I have to take my entire 5 variable function. I have to substitute whenever I find a variable by 0. Okay, that function must be multiplied with a complement so that the function cannot be changed. That's what you have to remember. And again, we have to consider a as an uncomplemented fashion, but without changing its value, what we have to do, we have to place logic 1 wherever you find the variable a, okay, and B comma C comma D comma E, right? So what we can identify from this one? What we can identify from this one? That means that it is simply 2x1 multiplexer. Am I right? It is simply a 2x1 multiplexer. So I can simply write it in this way. So for better understanding, I'll write it in this way. So it is nothing but a complement into f of 0, for example, and a into f of 1, right? Is it clear? It's simply a 2x1 multiplexer. So that means that we have to consider a 2x1 multiplexer of for a control variable is nothing but a. If it is 0, if it is 1. If it is 0, f0 will come into the picture. If it is 1, f1 will be come into the picture. So what is the f0 and f1? Any guess? It is nothing but a 4 variable function. Okay, it is nothing but 4 variable function. It is also nothing but 4 variable function. Are you agree with me?
sir.
This is input of this one, this is input of this one. We will find now f of a comma b comma c comma d comma e, right? So therefore, what is the note I am saying that what we can identify from this one? What is the note here? The note is that, so if you want to decompose the 5 variable function into a 4 variable function, then it requires two 4 variable functions. Okay, two variable function, two 4 variable functions, and but I'll write it as two 4 variable functions plus one 2 plus 1 marks. That's what we can conclude here. 1 2 cross 1 marks. Clear? Now, for example, if I ask you that, so if I want to convert 5, not 5 variable, not 4 variable, for example, 3 variable, for example, I have a 5 variable function is there, 5 variable. I want to convert into 3 variable, for example, not 4 variable, it's a 3 variable. Then how many number of 3 variable functions are there and how many number of 2 plus 1 multiplexers are there? Any guess? What does it mean? F of a comma b comma c comma d comma e. I have a function I want to do with the help of 5 variable function, so must be converted into 3 variable. So I can consider it
Four and two marks.
c comma d comma e. I can consider a and b are the selective variables. So in this case, how do we generate this f0, f1, something like that? Any guess from the class?
Then we need four three variable functions and 3 marks.
Exactly. So let us see how it is. So we have to choose, first of all, we have to decompose the 5 variable into 4 variable first, and from the 4 variable to 3 variable that we have to do it. So that is the best choice. So therefore what I have to do here is that first I want to convert this one into 4 variable first of all. Nothing but f of a comma b comma, so something like this. I'll write it at the bottom. So first of all, f of a comma b comma c comma d comma a 5 variable function is decomposed into, based on a complement into function of 0 comma, okay, b comma c comma d comma e. Fine. Next, a is multiplied with 1 comma a comma, sorry, b comma c comma d comma e, right? So that's how. Now what I have done so far, I have used the 4 variable function. Now each and every 4 variable function must be converted into again 3 variable. So how do we do this one? Something like this. So a complement into, so this is the function. Actually this function I can simply write it in this way. B I'm going to consider as an output. So a selection variable or decomposition variable. Normally technically we can call it as a decomposition variable. B complement dot f of 0 comma 0, in place of b 0 I'm writing c comma d comma e, right, plus b is multiplied with f of 0 comma 1. In case of b 1 we are writing now, b comma c comma d comma e, right, plus this is one 4 variable function is converted into 3 variable function, something like this. Okay, it consisting of only 3 variables. Okay, again this will be converted again into a is multiplied with f of, can you please tell me what is this? So we are keeping b is aside, b complement into f of 1 comma 0 comma c comma d comma e, okay, plus b is multiplied with f of 1 comma 1 comma c comma d comma e. This is what we can do. Are you agree with me? So therefore, what I can write it now simply in this way is that, so I can substitute inside of this one, okay, a complement into b complement into, this is as simple as I'll write it as f of 0. I can write it in this way. This entire function I'm writing it as f of 0, right? Next, plus a complement is multiplied to the b as well, and this is called f1. So in this function, a is 0, b is equal to 1. Okay, so that's what we have to identify. The third function, this function is a into b complement into f of, for example, 2. Let us consider here a is equal to 1, b is equal to 0. So again, a is inside, go inside of that one, a into b into f3. 3 let us consider. So something like this I have to do in this way. Okay, so for example, if I want to convert a 5 variable into 3 variable, this is the method. Okay, so what it has to do is that, we have to take the two variables as a decomposition variables, and we have to calculate the f0, f1, f2, f3, and make use of that connections, and then we can develop the hardware, right? Is it clear to all of you? That means, for example, I'll write it here, logical diagram. For example, this is a f0 will be generated here. Here we have to generate f1. Here we have to generate f2. Here we have to generate f3. So what is the f0? It is a function of b, c, d. Okay, sorry, is it a function of b, c, d or what? Not c, d, e. It is also a function of c, d, e. So like this, these are all the 3 input functions actually it is generating. Okay, so therefore, because I have since 3 variable functions, so again I have a 3 variable functions only available. So what I can do then, I have to consider 3 variable function for this one also. This 3 variable function is filled with this, the one thing, and a and b all are available outside. A, b is available here. So therefore, this is the 3 variable function, right? Again, I have to consider for another 3 variable function from this one, and take this is the one, z and b. I have to consider another variable for this one, and from a and b. Okay, and I'm going to consider another variable called a, b, and I have to use this one. Clear? Again, I have to consider a 3 variable function which must connect to this one, and this one. Again, I need to consider another variable called this one by using this one as well as this one. It is actually 3 variable. Therefore, one variable we are not going to use this one. Okay, not using this one. Finally, we have a function of a comma b comma c comma d comma e. That means you can observe very carefully. So this is actually 3 variable function. This also 3 variable function, 3 variable function, 3 variable function, functional block. We can call it as 3 variable functional block, 3 variable, 3 variable, 3 variable, and 3 variable. So that's how, whenever we have a 3 variable function generator, actually we can call it as a function generator or logical block. Okay, whenever we have a 3 variable functional block, that variables only, that function block only we are using to construct the 5 variable function, right? So this is allowed by using the technique called Shannon decomposition theorem. Is it clear to all of you what I'm doing here? It's a b something like this. Okay, so therefore, universally this is what happening. How many 3 input variables are required here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So okay, how many are there? 10 3 input function generators are used or required, we can say that. Clear? So therefore 10 function generators are required. So whereas here in this case, whereas in case of 4 variables, how many function generators are required? Any guess? How many function generators are required? General case I'm writing, general case we will discuss about this one. The later we come to the point of multiplexer utilization. Okay, for example, I have only the 4 variable functions are available. So what I can do here is that here, so one 4 variable function, another 4 variable function having something like this. So what are the inputs for this one? It is called B, C, D, E. B, C, D, E, right? So now we are going to use another not multiplexer, another 4 variable function generator. See, observe, 4 variable function generator, 4 variable function generator, 4 variable function generator. It considered this is the one input, this is another input, and the A is another input. So another one is vacant. Okay, we are not using this one, not used this one. So finally we got f of a comma b comma c comma d comma e, right? So therefore 4 variable function generators are used. Function generators are used. Okay, so but here how many are there? 10 function generators. So therefore it is advisable to reduce the number of function generators with the help of other things. Okay, of course, it is not necessary for all the time you have a 4 variable function generators or 3 variable function generators. There may be some associated, there may be some other function generators also available with you, like a multiplexer, for example, like a multiplexer. Okay, so therefore, instead of using, actually here, the resource is badly utilized here. The resource is badly utilized here. Why? How can you say that? Is a fourth input variable we are not using. As we have seen in the previous class, I show you that, for example, it is a 4 input to lookup table, for example, let us consider. If it is a 4 input lookup table, use the big logic circuitry that we have seen in the previous class. I will show you that one also for the sake of simplicity or understanding. Okay, so this one we have already seen. Okay, see here, it's a 4 variable function generator, for example. For this 4 variable function generator, so this much hardware is required in it. So since we are using only 3 variables, means only 8 possible combinations we are using, other 4 variable combinations we are not at all using, right? So that is the badly utilizing the resource utilization. Therefore, in order to reduce that one, what we have to do is that we can use other elements like multiplexers, Now effectively we can use this one. When compared to the cost of 4x1 multiplexer, 2x1 multiplexer is sufficient. Okay, therefore we can develop other logic circuitry, other logic functions whenever it is to reduce the hardware cost, right? So therefore what I can say that here I am using that, that is the reason why I can say that with the help of one multiplexer I can reduce one 4 variable function generator. Okay, whereas for example my requirement is that I have to only use the 3 variable function generator. Most of the cases I have to use the 3 variable function generator, but only we have to reduce the complexity by introducing the extra multiplexers. So how do we do this one? So a simple thing that I can tell you here, very simple notation. For example, general notation. For example, we have a 5 variable function. Carefully you have to understand. Note. For example, here I'll write it note. For example, 5 variable function. How many are the 4 variable functions are required? 2 4 variable function. Variable number 4. Okay, v underscore 4 is nothing but 4 variable function. Let us consider plus 1 multiplexer. Am I right? 1 multiplexer. Now I want to decompose this one by using, again, the 4 variable function is converted into 3 variable function. Then how do I do this one? 2 variables that is required, but I want to modify, that means I want to decompose the v of underscore 4. So by using the 3 variable. So can anybody tell me, for example, we have a 4 variable function is there. I want to convert to 3 variable. So is it clear? So how it is very easy to do this one. Just only 2 3 variable functions are required plus 1 multiplexer is required. As simple as that. Are you agree with me? So just for example, n you considered, if you want to go to n minus 1, okay, if n variable function is there, if you want to reduce by 1, that means less than 1 variable reduction, then this is what the scenario. Okay, so therefore what I have to do is that 2 n minus 1 blocks that are required, n minus 1 blocks are required associated with 1 multiplexer, 2 cross 1 multiplexer. Okay, the same applicable here also. So what I'm doing here, 2 v minus v underscore 3s are required plus 1 multiplexer is required, right? 1 multiplexer is required plus 1 is already available. Therefore what is the value is now here? So I have to multiply this inside of this one. 4 v underscore 3, 4 3 variable functions function generators are required, less 2 ones are 2 plus this is 1. So 3 2 cross 1 multiplexers are required. V underscore 3 plus 3 muxes. Is it clear to all of you what I have done so far? Is there any problem? Please let me know. So that means my requirement is that I don't want to use the 10 function generators, 3 input function generator. I want to reduce further that one. How do I do this one? So that's what, with the help of this decomposition theorem, according to the decomposition theorem, I have done like this. So how do I do this one? Let us consider it in this way. For example, I have a 4 input function generator. Okay, so let me draw this one also. So for 3 input function generator, 1 2 3, okay, and next one is 4. Clear? So here for example, that is for example, function of a comma b comma c comma d comma e, 5 input function. So I have yeah, so I want to consider only 3 input variable, means c d e. So the same inputs for this one, same input for this one, the same inputs also for this one, right? So I have a function generator, for example, f0. Let us consider this is f1, this is f2, this is called f3, right? So therefore what I'm doing is that, so there is no possibility we have to take 4 3 input variable function generator, there is no doubt, but here we have to use 3 multiplexers only. Okay, how do we do this one? Something like this. I'm going to consider one 2 cross 1 multiplexer here, another 2 cross 1 multiplexer here. So this is a one input, this is another input, this is input for this one, this is another input for this one. I'm going to consider this is called B, for example. I'm going to consider this is for B. Again, I'm going to consider 2 cross 1 multiplexer that is based on A. So this is the input for this one, this is the input for this one. Therefore, this is a mux, this is a mux, this is a 2 cross 1 mux. So this is a 3 variable function generator. Better I'll consider this as v underscore 3. V underscore 3. Is it clear how we have reduced the complexity hardware cost by using this particular decomposition theorem? So instead of using these function generators, this is 10 function generators, 3 input function generators are used in this case. Okay, that is possible to reduce with the help of multiplexers. With the help of multiplexers, just we are assuming that the multiplexers are also available with us. For example, if the multiplexers are not available with us, then ultimately we have to consider the 3 input variable only. Okay, so that is how this particular concept is very much useful whenever you are realizing the functions in FPGAs. Okay, so that means each and every functional block. For example, what is the basic idea behind the FPGAs? FPGAs consisting of CLBs, right? So CLBs is nothing but a configurable logic block or combinatorial logic block, one and the same. Okay, so CLBs that are available. What is the heart of the CLBs? It is a function generators. What do you mean by function generator? Function generator. So function generators are nothing but lookup tables, logical block or logical block. We can call it as a logical block, logical block. So technically some people will call it as logical block is nothing but a LUT, lookup tables. Okay, so one and the same. We can call it as this one or this one or this one or this one. Function generator, logical block, LUT, one and the same. So therefore, the size of the LUT is very fixed quantity actually. Okay, some FPGAs has three input LUTs are there. Some FPGAs has got the four input LUTs are there. Some FPGAs has got 65 input LUTs are there. Okay, therefore, whenever you are writing the program, so we have to map that program. We have to map that design into the FPGA resources. Okay, if the FPGA resources consisting of three input variables, then we have to convert our program, or we have to map our program according to the three variable function of the FPGA only. Okay, so therefore, in the translation, in the mapping translation, normally we'll follow the decomposition theorem, right? So therefore, this is what the important concept behind this one. Okay, so let us consider some examples. How do we implement these functions with the help of in terms of the lookup tables? Okay, so far we have seen the theory behind the how do we use the Shannon expansion theorem. Okay, now let us apply the same concept to the lookup tables. Okay, so let us take an example. Okay, for example, I have a function something like this. I'll take some example function. Uh, for example, this is about the function. Copy and then paste it here. Can anybody tell me what is the size of this function? What is the, how many number of variables are there in it? Z is a function I have given. How many number of variables are there?
6, sir.
Yeah, exactly. It is a 6 variables. So we have to identify some min term consisting of all the variables. Okay, so therefore this is the min term that suggested that the possible that are the possible variables. Therefore, it is actually Z is actually a variable A, B, C, D, E, F. So 6 variables are there. Okay, so I want to convert the 6 variable into 5 variable function. 5 variable function. Okay, 5 variable functions. Why? Because let us consider I have only 5 input lookup tables. LUTs. I have a 5 input lookup table is only available with me. What is the lookup table we have discussed in the previous class? Please go through that lecture once, therefore you can understand what exactly the meaning of lookup table. I have a 4 input lookup table is available with me, but I want to implement a 6 variable function. How do I do this one? So simply we have to apply the Shannon expansion theorem. What is saying that? It says that Z of, I can write it, Z of A comma B comma C comma D comma E comma F is nothing but A I want to consider as outside. A complement is multiplied with Z of 0. I have to put it 0. B comma C comma D comma E comma F. Okay. Similarly, I have to consider A of Z of 1 comma B comma C comma D comma E comma F. Okay, now what is the value of this this value? What is this function says that? So this is the one. Okay, so for this function, okay, so what is the value of Z of? Let us consider, for example, Z naught. Let us consider this is called A into Z1. Okay, So assume that I have only 5 input lookup table, no other elements are there with me. So then what is the value of the Z naught? What is Z naught? Z naught is nothing but take the value. What is the value is here? First one is A, B, C, D complement, E, F complement plus A complement, B complement, C complement, D, F complement plus B complement, C, D, E complement, F, right? Last one is F, not F complement, F only. Okay, just I have to place the 0 in case of A, this is 0. Therefore, here is 0, 0 complement. Any other way, no other thing. So what is Z naught here now? This first term is 0. The second term is B complement, C complement, D complement, E complement, F complement. The second one is B, C, D, E, F. So therefore, this is what actually is Z naught. So this is the function. It is this is the function. It is generated by the function generator. Clear? It is a function. So that means I have to consider a variable for 5 input lookup table. Okay, LUT5 we normally consider. So what are the inputs for this one? B, C, D, E, and F. What will produce? Z naught. So what is the inside of this 5 input lookup table? Can anybody guess me what is the how many number of SRAM shells used? Last class we have discussed. Can anybody tell me how many number of SRAM shells are there in the 5 input lookup table? Anyone from the class? The question
Sir,
is,
2 power 5, sir.
yeah, exactly. So how many are there? 2 power 5 possible outputs that we'll have. Therefore, 2 power 5 SRAM shells are there. Very good. Okay, somehow it will be generated according to the output will be available in that one. According to it will take that one. Okay, so similarly, so let us consider for Z1. What is the Z1? The same thing. Um, I want to copy this one if you don't mind. Okay. Copy and then paste it here. Sometimes my laptop is not working properly. Okay, therefore it is actually Z0. Sorry, Z1. It is a Z1. It's not A actually. It's better I have to remove this one. Okay, instead of now it is 1 I have to replace, right? So in place of A, 1 I have to write. Here in place of A, 1 I need to write. No, A is not there in that one. So again I have to write. So B, C, D complement, E, F complement plus this is 0 plus B complement C, D, E complement F. Are you agree with me for Z1? So therefore it is also a 5 variable function. It will produce Z1. 1, 2, 3, 4, 5. Okay, B, C, D, E, F. Fine. Now what is the final conclusion for about this one? I have to generate my Z based on A complement into Z0, A into Z, right? Z1. So therefore, I can simply write here is 5 variable lookup table. Here is how many number of lookup tables are required for simplicity. I'm asking the question. How many number of LUTs are required? 5 input LUTs are required. Any guess? How many number of 5 input LUTs are required? Okay, simple. So already we know already about this one. This is a 5 input lookup table. Okay, 5 input lookup table. This is obviously for the Z1. It is LUT underscore 5, the second LUT. Okay, So therefore 5 LUTs are required. So sorry, 5 input LUTs are required. But here we need to convert again to Z0 for Z1. I have to consider another 5 input LUT, LUT underscore 5. Okay, this is also LUT underscore 5. This is also LUT underscore 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So, but here is a 5 input LUT, other three inputs, 1, 2, 3, we are not at all using. Okay, because since I'm saying that I have only the five input LUTs, no other thing, right? So therefore I can say that 5 input LUTs are available, are required. Later point of time they have realized, of course, if at this particular instant of the time we have only at the last stage, the 2x1 multiplexer is sufficient. Therefore the FPGA, different FPGA vendors come with an idea of, I don't want to use a 5 input lookup table, this one, so I'm going to use an extra hardware like 2x1 multiplexers associated with the CLBs. In earlier days, the CLBs consisting of only the CLBs only consisting of LUTs, sorry, consisting of only LUTs and some flip-flops. Now the CLBs are manufactured, not only the LUTs, some additional logics. Some additional logics are also associated with this one, like multiplexers and all. Plus flip-flops are already available with that one. So therefore, that is how the CLB's the transformation has been takes place in order to better way of implementing the circuits with less number of hardware resource utilization, right? So therefore, with this, we have come to the end of the today's session. We will discuss the remaining things in the next class. Okay. So I have posted all the lectures in the YouTube, but only 3 or 4 lectures I didn't do that one. I will do it today. You please make use of that one. Okay. So because earlier I have a serious problem with the net